So welcome. In this video, we'll be working on the LCD with a I2C interface and a joystick module to basically we want to control the characters displayed in our LCD using a joystick. So with this project, you'll be working on with the different peripherals with the STM32, basically um, the I2C communication, the ADC mode, basically multi ADC mode, and with DMA settings and an external interrupt. So the external interrupt I have covered a separate video for that one. Go ahead if you haven't watched that video. So in this project we'll be exploring the peripherals, basically the multi ADC mode and the I2C communication. So first thing I want to mention is that the LCD that I am using uh, is a 20 by 4 CD, and that basically means that it has 20 columns and 4 rows or lines. And this LCD mine is actually standalone. It doesn't have this I2C backpack module. This basically allows the LCD to have an I2C interface. So it really it basically shrinks the pins to only just 4 instead of how many are these, like 11. So this is an efficient way to really shrink the pins because there's a lot of pins in an LCD. So I highly recommend to buy this one if your LCD doesn't have one. And yeah, this just allows I2C communication. And yeah, I actually uh, bought this one separately because my LCD is standalone, doesn't have this backpack module. So um, yeah, but I bought it, and as you can see, I have connected it just using a breadboard. And another one we'll be using is a joystick. So this one, it has a 5 pins, and so yeah, we'll be using this one again to control the characters that will be displayed in the LCD. And to interface this with our STM32, we'll be needing we'll be configuring the ADC peripheral of our STM32. So first off, let's settle with the I2C. So go on to the uh, but before anything else, we want our sys to be enabled, so serial wire, so that it will allow us to debug our STM32 board. So yeah, just selecting the serial wire, it will allow that one. And um, first let's configure our I2C. So for the I2C, go on to the connectivity and select I2C1. So um, just select I2C. It might show in your window disable. Just select I2C, and these parameters will then show up. So these are the parameters for the I2C communication of our STM32. So um, normally this would work fine. It's default settings made by the STM32. The I2C speed mode will leave it as standard mode. The clock will leave it as a 100 kilohertz. And yeah, just leave it as is. And after selecting this one, this will enable the I2C1 lines of our STM32. And basically these two pins right here, the PB7 for the SDA or serial data, and the PB6 for the serial clock. So we'll be connecting our SDA and SCL of our I2C backpack module or LCD to these pins. So this is basically we want to connect it to this I2C bus. Yeah, for the I2C communication, and that's it for the I2C setup. So the STM32 Cube MX really does make configuring or setting up easy. So yeah, we have to thank that one. And that's it for the I2C. And another thing, again, I mentioned that we are using a joystick module. So uh, joystick module inside the joystick module is just like a two 10K potentiometer. So let's take a look at um, the schematic of our joystick module. So I just search in the Google and this will show up the schematic. So um, let me just open this image new tab. So as you can see, the two main pins of our joystick module is the VRX and the VRY. So this basically tells us the x-axis position of our joystick and the y-axis position of our joystick. And as you can see, it's just an input from our two of our 10K potentiometer right here. I don't know the exact value of the potentiometer. I do know that it's like around 10K. Yeah, the common resistance value is 10K. So yeah, by like moving your joystick up, down, or left or right, or any direction, it will have a certain value of the x and y position, and this will only be determined using the ADC mode of our STM32. And I would also like to take note that the joystick module actually has a button on it. So once you press the joystick module, like the joystick like the joystick you call this thing once you move the joystick and like press it down, you will like hear a click, a tick, a button tick. So that is embedded in the joystick module, and as you can see, once pressed, it will short to ground. So that's a handy information that we want to know because we'll be needing the switch of the joystick module um, to switch modes. I'll explain it later. So will be these three pins are the focus of our joystick module. So let's first enable our analog or ADC. So I selected ADC one, and as I've mentioned, there are two analog inputs from our joystick module, which is the VRX and the VRY, or X position data and the Y position data. So we'll be needing two channels or in two input channels, input 0 and input 1. And these parameters will then show up. So here's there's a lot of configuration that needs to be done in the ADC. There's a lot of parameters right here. So basically, for the mode, for the clock prescaler, we'll just leave it as is, and as well as the resolution. As you can see, we just use the 12 bits resolution of our ADC, and as for the 12 bits resolution, we'll be needing 15 ADC clock cycles. So um, just take note of that because it will be needed to in another parameters here. And the data alignment, we will just leave it to right alignment because we don't want to shift our input data. And our scan conversion mode, let's enable it because we want that our uh, after channel is channel has done on its conversion, it will then switch to the other channel to to process the conversion. And for the continuous and discontinuous conversion, we'll leave it as disabled because we'll be needing a timer for our ADC conversion, and not need using a timer peripheral is found to be dangerous, and or it will lead to a unstable data. And for the DMA, again, we'll be needing DMA for this one. Basically, we want our ADC converted data to be directly stored to our DMA. And in order us to do that, we need to enable the DMA continuous request. And yeah, this just basically allows us to directly store the data, and will yeah, it will just automatically do itself, and we will not worry on different things. And for the end of conversion selection, uh, as mentioned, we will be needing two input channels, so we want all conversions to be done in order for, before it will raise the EOC flag. Then here for the ADC regular conversion mode, again we'll be needing two input channels, so we will we will enter two here. And for the external trigger conversion source, so again we'll be using a timer peripheral, specifically the timer 2, um, and this will trigger and yeah, it will be used for the ADC conversion. And for the external trigger conversion mode, we'll just leave it at the rising edge. And here we will then rank or give priority to our input channels on which which input channel we should convert first, then the other one, or give priority to it. So uh, normally this doesn't really uh, like greatly affect on the how fast it would reconvert. Uh, it's just that the microcontroller wants like an instruction to which uh, input channel, or yeah, ADC channel to convert first. So I just leave, or I just enter the channel 0 as first priority or first rank, and yeah, select channel 0. And the stamping time is 15 cycles, because again we selected 12 bits resolution right here, and it needs 15 ADC clock cycles for that. So select 15 cycles. And for the rank 2 is the channel 1 or input 1, and again 15 cycles. And for the ADC injected conversion mode in the watchdog, we just leave it as is, its default settings. And that's it for the ADC. And if you have enabled this input 0, input 1, you should notice that um, the pins right here is assigned uh, respectively for the ADC1 input 0 and input 1, so PA0 and PA1. So we'll be connecting our uh, joystick VRX and VRY right here. So, and that's it for the analog. No, actually we need to enable the ADC channels. So click enable here in the NVIC or the interrupt controller. And for the DMA settings, again we'll be using the DMA settings, so we'll need to click add on this one. So uh, basically, I've already added one ADC DMA request for the ADC1. So just click add, and these parameters will then show up. So the default mode right here is normal, but we want it to be circular, because basically want like a one memory address that will be continuously changed, and on what's the current conversion data. So like bit 0, I mean memory address, let's say 1, will be continuously changing its data depending on the converted data. And we don't want the normal mode, because it will selecting the normal mode will increment memory per converted data. So for we don't really need to have a record or of our ADC converted data. Just really want to have the data at that specific moment. So circular would be really practical and memory efficient. So here we will be selecting the memory, and the data width is word here as well. So that's it for the DMA request or DMA settings. And yeah, hit add. And yeah, again, enable these the ADC and the DMA tool. So along with that, we need this will yeah, this will automatically register the DMA request upon doing this one. So and lastly, so that's it for the analog. Again, these are the pins on it. Just remember the pins assigned because we'll be needing it to determine which pin in our pin header where will we connect um our joystick pins. So lastly, again, I mentioned that we'll be needing to use the button. So uh, we'll be needing the button because in our control for the LCD, we will have like two modes. One, we'll be needing this button of the joystick module so that we have like two modes for controlling the character display. So everything will make sense later on the code or and the display itself. So just take note of that. And with the button, joystick button, we will uh, configure it as a external input, external interrupt input to be exact. And the way we do that, it's just like any of these buttons really. Um, although yeah, any pins actually, any pins has a that has a peripheral to allow external interrupt. So as you can see here, it's I have set it as external interrupt, and then it will then show up right here the PC3. I've selected the PC3 as an external interrupt, and if you click right here, um, I have um, selected the falling edge trigger. Falling edge trigger is because again, let's go back to the schematic. Uh, we'll be connecting this pin to a certain pin, but it will remain uh, in a floating state because yeah, it's basically open, and we want to and once we press this one, it will then connect to ground. So another way to do this is we want to have like a pull-up resistor right here, but luckily the STM32 pins have like a configuration to select pull up and pull down. So I've selected the pull up right here. So basically it is high when the button is not pressed, and it will go low once the button is pressed. So that's it for the external interrupt for our button. And yeah, I think that's it for the setup for our STM32 cube MX. Oh, actually, for the timers, timer 2, yeah, for the timer 6, we'll be needing another yeah, for the both of the the timer 2, I have set the prescaler at 17999 and the counter period reload auto reload register to 100. So basically I want that our timer to have like our clock configuration. Our clock is 180 megahertz, and I want to run our timer 2 for around like 100 hertz. Let me just grab my calculator. Forgot why I put this data. Sorry. So the formula actually to generate a like a frequency of a specific timer is that is the clock configuration clock data right here. So 180 megahertz over 1799, or the prescaler times the counter period. So 180 megahertz. So and the prescaler value is 17999. This is actually, let me just do this. This is actually uh 18,000. But based on the data sheet, we need to subtract it one. So let me just like explicitly enter here in the -1 so that I won't forget. And what we are doing right here is this configuration allows um, a let me just take a look. I'm doing, yeah. So this configuration allows 10 hertz of clock. Because the reason why I wanted 10 hertz is I want the timer or the ADC conversion to run at like every 100 millisecond. So yeah, I you could really make it fast, but I think 10 hertz is quite reasonable because I mean in our project time critical is really not a factor. So and that's it for the timer. Timer 2 is again for the AD's conversion, and for the timer 6, I enabled another timer. This is for the debounce. I don't even know this, but buttons have like a mechanical debounce, a bounce whenever you press on them, and like the moment that you press the button, uh, it is really not stable at like the first like milliseconds, like first 1 to 5 milliseconds. So the value or the state is not really again stable. So we want like after 5 seconds or 10 milliseconds, that's when we capture or get the value or of the value or the state of the button. So I want to like I have allocated a 50 milliseconds the bounce time for it. So again, uh, the way you want to do or calculate the prescaler is that the clock configuration 180 megahertz divided by the prescaler times the counter period or the auto reload register. So let me just do my calculator once again. 180 megahertz. Yeah, divided by or over by the prescaler. Oh, so actually this is 89999. So 9,000 minus 1 times 50. And this should have, wait. Oh, I'm sorry, but the timer 6 and timer 2 is actually running at 90 megahertz because the APV, the timer 2 and timer 1 and timer 6 is connected at the 90 megahertz. So yeah, you could really scale down this to 90 megahertz. I'm sorry, I'm really like all over the place, but yeah, I'm I was just early done coding with the this project, so I kind of forgot what I did on the setup. But yeah, there's a lot of parameters that you needs to deal with, so bear with me. Um, so what was it? Yeah, one. So running one in 180 megahertz, but it will then like divided by two here on the APB1. So I'll leave it to you guys in your data sheet on which um, timer 2 or timer 6 is located. So in my chipset, the STM32 F446RE, it is located at the APB1. So it will then, having a 180 megahertz clock right here, will result to an 90 megahertz. So what I the calculation here, what I did here is really wrong. So this is actually 90 megahertz divided by uh 1800 times 100. So it will have like a 50 hertz clock frequency. So that will result to clock tick per 20 milliseconds. So that's quite fast. Because we are yeah, we don't really need a fast ADC conversion. Yeah, it's really up to you or a matter of preference. But yeah, we'll just use the speed in our own hands. And for the timer 6, again, I want the bounce time for around 50 milliseconds. So um, our so let's calculate again. 9,000 90 megahertz again, 90 megahertz. Uh, then over 9,000 times 50. So I have here at 200 hertz. Wait, let me just check my calculation. Yeah, 9,000. Yeah, 200 hertz. Then this should result to a, yeah, 50 milliseconds um per clock tick. And we want to really trigger the um in yeah, we want to have an interrupt right here. So we want to enable hit the timer 6. And for the timer 2, I forgot that for the ADC conversion, we want to select the trigger event selection update event. And yes, that's it. I hope I don't really confuse you guys on the setup. Don't you worry, I'll be um, also including this setup configuration, the STM32 MX setup configuration, and yeah, in my GitHub. So yeah, hit generate code, and this will then launch you with the Kale project. So now that we are in our Kale IDE, so as you head on to the main file, you can see that the STM32 Cube MX already handled all the type handlers for our ADC and DMA and I2C, and as well as the initialization using the HAL API. And right here, just a heads up, for the LCD, with the I2C communication, I have created a separate file for it. Um, yeah, basically it is a, yeah, you could call it a library, I guess, for LCD commands or functions. So it contains here all necessary functions to display a character in the LCD using the I2C, and yeah, and as well as the setup, initialization, and yeah, I've actually just um, found this online and I just configured it in a way that it would work with a 20 by 4 LCD. So yeah, just this disclaimer that um, this C file for LCD right here just only works for 20 by 4, but it is not that hard to configure it to, like, let's say if you're working on with a 16 by 2 LCD. So yeah, I'll be including this in the description. I'll probably set a repository in the GitHub for this one. So, anyways, as you can see with the project, I'm working with a joystick for the ADC and the I2C LCD to display our characters, and um, the LCD has you can maneuver it in XY position, and depending on the XY position, we can um, set yeah, work what mode on it. And let me just explain the code right here. So I'll go back the global variables right here in a second. So again, the HAL is initialization by the STM32 and all the peripherals initialization. And here we began the timer based start. So again, for the ADC communication, we have set the timer to as um yeah, the source of for the timing conversion. So we have start using its base. So include this one. And for the DMA, yeah, you need to start it as well because again, we want our ADC conversion, ADC input data from our joystick to directly store into a memory, bypassing the let's yeah, technically bypassing the CPU process. And yeah, just passing the pointer for our the handler of our ADC1, and the second parameter is for the value where we want to store the ADC. So I have declared here the variable which is a an unsigned integer 32-bit, but this could work with 16 because again the ADC has a 12-bit resolution. So yeah, I just put it 32, and 2 for yeah, the length, because yeah, there the what do you call this? I have only 2 bytes. Yes, 2 bytes. Not 2 bytes. Basically two ADC values. So here's the size with that one. So pass in two because again, one is for the X position and the other one is for the Y position. And here we call a function for our LCD file, and this is for the initialization, right? So here for the initialization, let me just zoom it. So I wish I just have opened the data sheet of the LCD, but anyway, I think I'll be working on a different video for this one for the LCD. So according to the data sheet for initialization, by the way, with using by well using the PCF 8574 I2C backpack, it is configured as 4-bit initialization or 4-bit data line. So we need to inform the LCD of that one that will be using 4-bit um, data transmission. So according to the data sheet, we need to pass this commands. I mean, data's right here, and this LCD send command uh, is actually again, which takes a character CMD as a parameter, and again we are working with the only the upper upper nibble or of the byte. So we have masked it here, and yeah, store a separate variable for the upper nibble and another one for the lower nibble, because we want to pass it yeah, there's essentially like 4 bytes to be passed in this configuration as a 4-bit transmission. One is for the yeah the upper data needs to be transmit, but there's a yeah, according to the data sheet, you need to pass on like you need to toggle the enable line during transmission, and but it will be done here by the I2C master transmit. And yeah, here the data T. So yeah, just passing on the array, the pointer of the array, and it will send these bytes sequentially. And yeah, oh, it's just the HAL I2C library that will do the job. You can further look on to this if you want to, like the bare metal programming on this one. Just right click on this one and go to definition. But this yeah, I'll be just briefly explaining on that one. And that's it for the command. So there are a lot of commands that uh, can be found in the datasheet, and which I'll be talking on a separate video. That's for sure. And yeah, we according to the timing diagram, there are some certain timing or yeah, delays that needs to be done. And yeah, and for and here for the display, so this block of code is for the display is display initialization. So we want our LCD again to function as a 4-bit mode. Um, and this is exactly for line display. Let me just change that one. And yeah, the character resolution is 5 by 8 uh, dot matrix, something like that. And yeah, every command there's a 1 millisecond delay, and another LCD configuration is for the display on or off. But at this particular moment, we want to turn it off, as it is a part of the step to initialization. So display on and off, display off first, then clear display. Then we want to display. I mean the entry mode set. We want to increment it, of course, per per addition of a character, and there's no shift. So, and another configuration here is to display the LCD. And this time we want our cursor to be displayed. It is up to you. It is a matter of preference. I just want to um, display the cursor so that I can know where the in which like particular cell in the LCD is my yeah, what particular address where am I at. So a cursor, a visible cursor, would be definitely helpful. And I just disable the blink, and that's it for the initialization. And that's what is being done right here. And the put cursor. So this is actually the part where we want to like pinpoint the position of our character. So in here, this function right here, um, so basically I am working with a 20 by 4 LCD again, and that just means 20 columns and 4 rows or 4 lines. And by passing on the row and column right here, I have set a switch case for the row. And these are the initial or the offset address for per each line. So for the first line or for the first row, this the address or the DDRAM address for that one is hex 0. And the next line or the uh, yeah, the next line is the hex 40 and hex 14, then hex 54. And you might notice that this is plus equals because depending on the column that we want to display or display the cursor, we want to add it on the base or the offset of the row. And this will make sense later on. I'll break it down per like mode. I'll run, then configure the code, and run, configure the code. Yeah, you'll know what exactly I mean. And yeah, and this is then or equals to 0x80. So this function right here, this byte right here, what essentially it is essentially an instruction in the LCD datasheet that we want to have the most significant bit of the byte to be 1 if you want to like modify the position of the character in the LCD. Uh, Basically, we want to have change the position of our cursor, and that's it for the LCD put cursor. And yeah, so this basically means that in the first row and the first column, we want to display the string joystick. And this function right here, the LCD send string, um, is a function that takes a character pointer, um, and basically it continuously it dereference it, and whenever it doesn't found this kind of like this kind of character, which is like null terminator. I'm not quite sure it is this one or this one. Kind of forgot that, but this is like a string terminator, and this is like a false value, has a false value. So whenever do we dereference it, yeah, we continuously run this send data function right here. If the reference value or the reference character is not this one, so yeah, it continuously send the data uh, and increment it until it won't until this one will show up. And yeah, the address of the string that is being passed on will continuously being incremented. And this LCD send data right here has the same configuration in sending commands. It's just that the reset is active high in this manner. So yeah, same thing. You want to separate the upper nibble or the upper byte, the upper nibble and the lower nibble of the byte, and because we are in a 4-bit mode transmission. And so that's it for the send string. And you know and then here in the second line, because it is in one already, yeah, I basically have a message in initial setup, and this will display for about 1 second, and then it will clear. And this is it will then enter our main while loop. So here in our main while loop, um, we continuously set our LCD put cursor uh, on what's the current value of our row position and call position. And at the moment, at initially, it will have a value of 0 because I have set the value 0 right here in initially. and and also I mentioned that we are using the button of the joystick, and we set it as an external interrupt for that one. And basically what is basically if the joystick button status is pressed, so let me just head on to the callback. So I have callback of the um external interrupt right here. Where was it? Here. So this is an external callback of the button. And you might wonder where the heck did I get this function. Is actually found here. So as you might already know, there's a specific file for interrupt or ISR routines file, and this is the STM32 F4 underscore IT. But the problem in this one is that we can't pass on data from our main, so which is why we use callbacks. And how I discovered callbacks is if you go on to the definition or go on to the file definition of this the interrupt handler right here. So go to definition. It take a while, and as you can see there, it has this function, this this callback. But as of the moment, it is unused and it has a weak type, so it's basically useless. And this is done by the ST so that it allows us users to either use this one or not. So I just basically copy paste this one, copy and then paste here, and I change the type to void. And yeah, this will be called upon entering this interrupt handler. And yeah, I have start the timer. So this timer is again timer 6 is intended for the bounce. So upon clicking the button, again, there's this mechanical debounce, and we want to only get the value or get the status of the button after 50 milliseconds upon pressed. So upon so it will start an interrupt of the timer 6. So again, I have configured the prescaler and the auto reload value on that one, so that it will interrupt per 15 milliseconds. And like any in like any peripheral or peripheral interrupts, it has a callback, just like the external interrupt right here. So the I have called again a callback for that one, and this is here, this one right here. And same thing, I've discovered this on the interrupt file right here, listing all the ISRs, and here, and you can go to the definition of this one, and you will find a weak function, weak callback function. And I just copy pasted that one, and this is like the HAL timer period elapse callback. and And of course, this is like a general for timer uh, callbacks. So we have a condition right here that if the uh, timer handler that triggers the callback is the timer 6, we want to stop the timer, because again, it's after we want. There's no reason for it to continue, because you only want the 50 milliseconds. And we stop the timer because we want to resume it every time the button is pressed. So yeah, upon the bounce time, it will stop. Then up, then we will then read the status. That's the time we want to read the status of our button. And if it's still like again, the button is active low, then that's the time we want to toggle our LED. So this LED indicator is just like a preference to me. I want like an visual indicator if the button is pressed. So I toggled here the LED, and I have toggled as well the joystick button status, and at the moment it is 0. So upon toggling it, like here, like this one, this is actually an XOR equal. So it will basically toggle the value of the joystick button status. So again, the current value of the joystick button status is 0. So then upon toggling, it will then it will then be set or equals to 1. So let's go back to our while loop. Um I know it's too much. It's actually a lot to take in, but uh, let's just discuss it step by step. So if the joystick button status is 1, it will then select the character selection mode. This is the part where whenever we move the joystick, it will sort of select the character. And I have programmed it in such a way that I can display not only alphabet characters, but also numbers. So I have created here a numeric. This is basically a flag. So at the moment it has a value of 0. So it will not come here. It will go here in the else. So let me just look on to the ASCII. I have quickly browsed an ASCII table right here. So basically, um what we are doing right here. So basically, LCD will display character depending on the ASCII table. So the reason why I have a value 65 right here is that again, our X count initially. So the X count is basically a character alphabet character selection. So Both y count and x count has an initial value of 0, and having a 0 right here plus 65 is of course 65, but it won't display the value 65 right here, but it will display the decimal 65 equivalent to the ASCII table. I mean, what do I mean by that is here in decimal 65, 65 right here, this decimal 65, its character equivalent in that one in the ASCII is capital A. And all the character symbols right here are the only values or the only characters that will be displayed in the LCD. So if I uh, if I pass in a parameter of decimal 65, it will basically display in the LCD the character A. So um, I'll show that later. Don't you worry. Um, yeah, I'm just like explaining why I have a value 65 right here. So basically, if I move the joystick in an X position to the right, it will continuously increment the X count. And let's say I have incremented it to the value of 5. So what is being selected in the alphabet or the character is 65 plus 5, which is 70. It will then display character F. So that's the algorithm for that. And the same thing for if we have uh, basically the X count is for the characters, the alphabet character selection, and the Y count, the Y axis is for the number selection. And if it is number selection, the base value or the base value for like the 0 is 48. We'll check that in the ASCII table if it's true. So decimal 48, yep, the character is 0. So if I move the y-axis let's say above for about 8 times, it will increment 8 times the y count, and then that's it will then add the value 48. So 8 plus 48 is 56. So it should have a value of 56, and that's the value of character 8. Character 8 will be displayed. So that's the algorithm for that one. And the way I program it in a way so that the microcontroller knows which are we choosing is I have again here I have a flag is numeric. So let's just move on, okay? We'll go back to this part right here where I you know configured or changed the value of the is numeric variable, and here is for the x-axis. So basically, ADC again we have a array that we pass on for our ADC DMA, and there are two. The size of this array is 2. Um, the first element is for the x-axis, and for the y-axis is the second element, or the one index. So these are the values. As you might expect in the ADC. Let me just check if I record. Yep, I forgive me. So normally in the 12-bit resolution ADC, so the values will range from 0 to 4096. Uh, where do I get the value of 4096? I know I know you might have known this, but just a quick refresher. So our microcontroller is a 12-bit ADC, has a 12-bit ADC resolution, so it can have a value to 0 to 4096, or 2 to the power of 12, which is 4096, which is I don't know actually 0 to 4095 because a 0 counts as 1. So yeah, you probably know that already, but just a quick refresher. So if we move our x-axis from the left, I mean from the right, which is the like the positive positive quadrant or positive side, it will have if we again we move it all the way to the right, it will have a value of over 3,300. That's the way we uh, determine that the joystick is maneuvered or like yeah, is in the direction of all the way to the right because it has a value over 3,300. And if we move all the way to the left, excuse me, it has a value of less than 100. So again, this is like moving all the way to the right has a value of over 3,300, which is usually 4,096, and all the way to the left. So this is usually close to zero. So that's the way we can determine the direction or where the joystick is being controlled to. And again, we want our x-axis to for the uh for the character selection. We want to select it the alphabet characters, and of course we are working on a flag right here. The reason for this flag is that what do you call this? Yeah, we want to display the I'll talk about that later because it really doesn't make sense at the moment. But yeah, at the moment it is being reset is numeric because again we are controlling the character selection because we are moving our joystick in an x-axis so to say. And yeah, just visual representation, I want to write or set the LED high whenever I do that, and I increment the X count, and uh, you know that the X count value will be displayed here. It will be sent, and and there's a limit of the X count. Basically, I would just want to filter out the alphabets in the ASCII. I don't want to reach the increment or the X count value to, let's say, right around here or yeah here. So which is why I have the value 57 and some delay, because if you don't put delay, it would really the LCD will be just like continuously on display, and we don't want that um uh because again we are working on a very fast microcontroller, and it might be not it might be too fast for us to really work on with. And the same thing for the if it is less than 100, the x-axis, so we are moving our joystick all the way to the left, so we are basically decrementing it. So all the way to the right we are incrementing it, and the all the way to the left is decrementing it. And if we have the set value of 0, we just want to like put it on the maximum value right away. And yeah, so basically if we are in the character selection of C, and if we decrement it, it will then have a value B. So, and let's move on to the y-axis. So for the y-axis it is numeric. So here I put the flag is numeric right here. So you might have already found out why I have the flag right here, because there's a different base value for the numbers and for the alphabet. So we will have a set a flag right here so that we can determine which the on which the joystick is currently maneuvering to, either in character selection or in numerical selection. So That's the reason for this flag is numeric. And the same algorithm for the x-axis. We just want that our values again, numbers is only set to limited to 0 to 9. So if it is the x count is beyond the 9, we just want to revert it back to 0. So same thing here to the x-axis. It's just basically decrementing if less than 100. And yeah, if anything else, it will turn the GPIO or the pin 5 to 0. So there's which indicates there's no activity at all or in default mode. So if the joystick button status or joystick button is not pressed or is toggled, that indicates the mode of let's just call this LCD position or address selection. So that's it. That's for the if we didn't press the button. So of course initially we have a value of 0 of the joystick button status if we didn't click the button. So it will enter this block of code. So as the comment suggests, it is like moving the cursor around in the LCD. So same thing, we have the x count and y count values, and if greater than 3,300 in the x-axis, we are continuously moving to the right. So um and yeah, continuously incrementing, and again we only have a we are working on a 20 by 4 LCD, so the limited is 0 to 9. The range is 0 to 19. So if it reaches above 19, it will then revert back to the first row, first column to 0. And if less than 100, we just basically decrement it. Excuse me. And yeah, we are just continuously moving to the moving the cursor to the left on this moment. And again, if there's no activity at all, we want to set it as 0. And for the ADC joystick value 3050, yeah, above, which means we want to move the row or navigate the row. So if above 3050, we are continuous like moving up the row. So if we are in the position 3, we just basically want to go back to the first line. So yeah, same thing here for the x-axis, y-axis below 100. We step backward in terms of row. So I know there's a lot of taken, but it's quite really simple. There's a lot of conditional statements that make this project work. So, and of course, I put some delay right here because if we are not doing anything, we just continuously sending this command right here, the LCD put cursor, depending on what's the value of the row position and column position. And it's better to have always a timing for that one or time delay so that it won't really continuously make the LCD busy. And I guess that's it for the this project. And uh I'll perform some tests in the project and the hardware, and I'll show it later. So basically we have covered ADC. Let's go back to the, yeah, we have covered DMA as well, the ADC and timers, external interrupts for the joystick, and yeah, ADC for the joystick, and DMA for storage, and external interrupt for the button, and I2C for the LCD display. So Yeah, that's it for the code. I'll upload this one in the GitHub, and let's upload this one and build it first, then load.